Hi guys, welcome to topic 8.4, where we are going to begin the process of predicting products after going through and classifying reaction types. So we know typically in the lab you start out with a given material, you put X and combine it with Y, and we're going to try to figure out what it is that is going to result from that reaction taking place. So there's going to be a blast from the past, and I've warned you guys that things do not go away in chemistry. So you need your periodic table with charges because chemical naming is now going to come back into this unit. And so some of you had a little bit of a rough time with chemical naming. And to be honest, I think some of you are relying a little bit heavily on Google, and Google is not always right. There's lots of different branches out there in chemistry. Some of you magically knew organic chemical naming for methane, for example, when we've never taught you organic naming, and you have not seen organic naming before this. So what I'm getting at is you need to be using the resources I'm providing to you. You need to be doing the work, not Google, because again, this is where it's really going to start to show and really start to affect your grade. So you need to take ownership of what you need to be doing to be successful, not what Google needs to be successful in Mrs. Moran's honor chemistry class. Okay, so if you don't have a periodic table of charges, go ahead and pause this video, get yours jotted up real quick, so that way you have it as we go through these examples. So we've introduced now 5 reaction types. One of the reaction types that we classified yesterday was synthesis. So where we're going to now is figuring out what a synthesis reaction is going to make based on the given reactants. So just as a refresher, a synthesis reaction is where you're taking 2 lighter substances and combining it into something heavier. Typically, it's elements combining into a compound, but you can take simpler compounds and combine them together into one compound. The one thing they all for sure have to happen is you end with one product, and that product is a compound. Now, I'm going to teach you basically kind of the first little inch in this topic, and that's how to predict the products of a binary system where it's ionic. Now, if you go on to take AP or go on to a college class, there are more types of synthesis reactions that exist, where what happens if you have a metal reacting with oxygen versus a non-metal with oxygen. And so we're not going to go down that rabbit hole with synthesis and decomposition. So there's more out there. I'm just giving you a taste of how to go about this process. So when we predict products of something that is for a synthesis reaction, the product that's going to result right now is we're going to say that it's a binary compound. So it's going to be made out of 2 things, and those 2 things are going to be a cation and an anion. So when we start, we need to translate or write the formula of the reactants if they're not provided. And we need to look out for these 7 elements called diatomics. So we saw these a little bit in our Lewis structures. I just didn't really call them outright as diatomics. So there are 7 elements that, because of their reactivity and configurations, they are always in pairs. So I have an acronym for you to remember that by, and that's Hoeffenkleyber. So Hoeffenkleyber stands for hydrogen, oxygen, fluorine, iodine, nitrogen, chlorine, and bromine. And so those are the 7 where hydrogen is never just H, but H2. Oxygen is always O2. Fluorine is F2. Iodine is I2. And you're probably catching the drift here. So these 7 elements are always paired with another one. You never have a single oxygen atom floating on its own or a hydrogen atom. They're always in pairs. When we look for our next part is what is the outcome of a reaction, we need to use ionic charge with our chemical naming, where we have our cation, anion, and following those rules. And then lastly, balancing. So we're throwing a lot of skills together now into one bigger picture. So these first 2 examples, I've already given you the symbols for the reaction. So what I have here is that this is calcium and sulfur. And so I can tell that it's going to only end in a synthesis reaction because I have 2 single elements on the reactant side. Now, when it comes to figuring out the product side, that's what we're working on today, is what is this reaction going to make? It's not as simple as you just put the 2 symbols together and you're done. You have to account for the fact that these are making an ionic bond, and they need to make something that is neutral. So this is where your handy dandy notebook, and by handy dandy notebook, I mean your periodic table, becomes useful. So we have calcium, which is a +2, combining with sulfur, which is a -2. Also, remember, order does matter. So when we go to figure out the formula of our product, we need to first of all remember that our cation goes first. So calcium is a +2 charge. The anion, the sulfur, is a -2 charge. And so that goes second. So we have a positive first, negative second. Looking at what happens to our charges, they cancel. So we get a formula of CaS. This is the product of this reaction. So in this instance, yes, we can just combine them together because it takes one calcium to neutralize one sulfur because of the +2 -2 scenario. So then the last thing we have to do is balance it, which if you look, it's 1 and 1, 1 and 1. You can write already balanced or fill in with ones, and we are done. So in the next example, we have magnesium combined with oxygen. Notice that this is O2. Oxygen is one of the 7 Hoffenklivers. It's one of the 7 diatomics, so oxygen on its own is always going to be O2. So we know we're going to combine a metal with a nonmetal. Like up above, you list out your metal first, the magnesium, and you need to know its charge. Utilizing the periodic table, magnesium is an alkaline earth metal. It's a +2 charge. Your anion always goes second. The anion is the oxygen. Oxygen is a -2 charge. So like up above, our charges have canceled. So our final formula is MgO once we simplify or cancel out those subscripts. So that is the outcome of this reaction. So again, notice that that 2 went away. So a lot of times students will say MgO2 is the product, and they forgot to account for the charges. So again, that 2 has disappeared. We now have an unbalanced reaction. That's when we then go in and add our coefficients. Our magnesiums are balanced. The oxygens are not. I have 2 on the reactant side, 1 on the product. Therefore, I need to put a coefficient of 2 on the product side. That changes my magnesium, and I now have a balanced equation. So we are now combining, again, many different topics together into our current new material. Now, the next 2, I give you the full names of your reactants. So before we can even begin looking at products, the first thing you have to do is translate this into your formulas. So going back, copper, if you remember, is in the D block of the periodic table. It's a transition metal. These were the ones that worked with Roman numerals because, again, they don't have fixed charges. So that tells us one thing. This copper 2 just tells me that when I get to the naming part of coming up with the formula, that's copper with a +2 charge. That doesn't impact anything on the reactant side. So when I go to translate this, I'm just going to draw a line for my coefficient for later on, and I'm going to put Cu for copper. Copper is not one of the 7 Hoffenklivers. It's not one of the 7 diatomics. Therefore, no subscript is needed. It's reacting with nitrogen in the atmosphere, so nitrogen is N. N, however, is one of the 7 Hoffenklivers, so it is diatomic. So the subscript is A2. That subscript will always be the same, no matter which of the 7 Hoffenklivers it's in. Diatomic, the di part means 2. So this is just like what we did up above. Now we're ready to figure out what did this reaction make. So again, I had to provide you with this Roman numeral because it's a transition metal. Now, to develop my product, copper is my cation, therefore nitrogen is my anion. Nitrogen is a -3 charge. So when you go to get your final formula and you cross down, nothing is simplifying, you get Cu3N2. So what I have here in blue needed to be done by taking what was above and translating it. I got what's here in purple by taking my cation and anion, using my information from the periodic table and this Roman numeral, to get my final subscripts. Now I'm at the point of balancing. Looks like my coppers are not balanced. A coefficient 3 will take care of that. And the nitrogens are balanced. You can write in ones here if you wish. And that is the third example for synthesis. So working on our next one, we have hydrogen plus oxygen. Hydrogen is H. You have to ask yourself, is it Hoffenkleiber? It's the very first one listed in the acronym, so it's H2, just like nitrogen was N2. Plus oxygen. Oxygen is also Hoffenkleiber, so it is O2. So from there, we need to figure out what these two things are going to make. So again, we're at the point of developing our product. To figure out what your product is going to be, you need to look up charges and cross accordingly. Hydrogen is here. It's a cation. It's a +1. Oxygen is O with a -2. Again, you leave subscripts behind. We're taking a +1 charge, combine it with a -2 charge. We cross our charges to get our subscripts, and we get H2O. Again, your subscripts are not going to match what is on the reactant side, and that's okay. That is when we then add coefficients to conserve and balance the mass out. Hydrogens are balanced, the oxygen are not. I need to add to my reactant side, or excuse me, the product side, because it's to the right of the arrow. A coefficient of 2 will fix that. That then alters my hydrogen. I need to adjust it on the reactant side. A coefficient of 2 will take care of that. And we are now balanced. So this is how you predict products for a synthesis reaction. So again, you need to look up charges, cross them through to get your product, and then balance them out. So from there, we have another reaction type, which is decomposition. We identified decomposition as the reverse of synthesis. If you just move these to the reactant side and this to the products, you're back to synthesis. So all we're doing is taking that compound and splitting it apart. So product prediction is going to be a little bit different because we're not writing a formula for a compound. We already have the compound. So here in their first example, we have NaCl, or sodium chloride. So I know that it's decomposition because it only has one reactant on the left-hand side. So I know that the only thing it can do is break down. So it breaks apart into its two elements, which we have sodium and chlorine. So those will be my two products of this reaction. So sodium is not in the 7 Hoffenkleibers, so it is not diatomic. Chlorine, however, is Hoffenkleiber, so it is Cl2. So all you need to do in decomposition is separate your cation from your anion. Again, there are more specialty ones out there. We aren't getting into those at this point, at this level of class. So then we just need to account for balancing. Sodium are balanced, chlorine are not. A coefficient of 2 on the reactant side will take care of that. We then need to adjust our sodium on the product side, and we now have a balanced equation. In the next example, we have aluminum and oxygen. Again, aluminum here is my cation. The oxygen is going to be my anion. So I just need to separate these out. Aluminum is not Hoffenkleiber, therefore there will be no subscript there. And then oxygen is Hoffenkleiber, so it will be O2. When you go to balance, you can start by balancing your aluminum. When you do that, you'll place a 2 here. I'm not going to do that because what I can see ahead of time is my oxygen are in this 3-2 situation where I'm going to end up with an odd number. Get rid of that odd number by placing a coefficient of 2 in the front here. That makes this 6 oxygen. So on the product side, I need a 3. That changes this to 4 aluminum. Therefore, I need 4 on the product side, and I'm now balanced. Now, when it comes to predicting your products for decomposition, for example, it does not have to go in this order. You could also say this as well. These are the exact same thing. So when it comes to predicting the products, it doesn't matter which product you put first. You can put the metal first or the non-metal first. So again, in this case, I swapped the oxygen to being the first product and the aluminum to being the second product. So again, in your compound, it matters. The cation has to go first, anion second. But when they are separated out into their own elements, the order does not matter. I just tend to write the metal first because that's what I see first. Okay, so the next two have formulas, and we need to translate it into our name to a formula. So we have silver 1 nitride. Again, silver is a transition metal. That is the charge of the silver. So that's Ag plus 1. Nitride with that "ide" ending tells me that it is not a polyatomic, but it is nitrogen from the periodic table, which has a -3 charge. Just like up above, once you've done that, you cross down, and our final formula is Ag3N. We now have our reactant. So starting our formula, we have Ag3N, and we're going to look at what it yields. Well, we can kind of see that by what we just did up here with figuring out our charges to get our formula. So we're going to separate it into our two elements, silver and nitrogen. Silver is not Hoffenkleiber, nitrogen is, so we have Ag plus N2. The last step then is to go through and balance the equation. Looking at what we have, the silver are not balanced, but neither are their nitrogen. If I balance the silver, that's fine, but then I'm going to have to change my coefficient here to balance the nitrogen, so I'm going to skip that. I'm going to place a coefficient 2 here. When I do that, that changes my silver to 6. Therefore, a coefficient of 6 on the product side and a 1 or leaving it blank on the nitrogen will balance that reaction. So the last one with decomposition is beryllium phosphide. Beryllium phosphide, we know beryllium is Be. Taking a look at your periodic table, it's a +2 cation. Phosphide means phosphorus with a -3 charge. Go ahead and cross your charges down. And your final formula here is Be3P2, and nothing can simplify. We now have our reactant. And we know what our two elements are. So again, you can write them in either order. I'll go ahead and write phosphorus first on this one to just change things up and put the beryllium second. Again, the reason why order doesn't matter here is because they are not in a compound together. So the next thing is, are either one of these Hoffenkleiber? And the answer is no. So neither one of them requires that subscript. Now we're just at the point of balancing. Beryllium is going to need a 3 on the product side. Phosphorus will need a 2 on the product side. And we're going to keep a 1 on the reactant side. And we are done. So what I've gotten at so far with synthesis and decomposition is that you need to make sure that you're accounting for charges when you go to make your product in a synthesis reaction. If you are needing to write the formula out for your compound and decomposition, same thing. You need your charges and then break it apart and make sure that you account for Hoffenkleibers and then balance. So there's one last reaction type we're going to look at today, and that's combustion. Single replacement and decomposition have a lot more detail that go with them, and we'll get into those more and we'll specialize those out later on. We're just going to lump these three together because synthesis and decomposition are so similar to one another, and combustion's pretty easy. So combustion has 3 parts. The first thing is we always have a hydrocarbon. So that's the first part. This X and Y just means that you can substitute in different subscripts. So the first thing is if you see a hydrocarbon as a reactant, so some combination of carbon and hydrogen, and its next requirement is oxygen. So in order for something to combust, you need oxygen present. The third and final thing that points out that it's combustion is you always make the same product each and every time. You always produce carbon dioxide and you always produce water. So basically the only thing that swaps from one combustion reaction to the next are the subscripts that you see on the C and the H. Therefore, that changes the coefficients required to balance. So here, for example, with our naming system that I've taught you so far, this is called carbon tetrahydride. Now, if you're an organic chemist, that's called methane. But what I can see is this is a hydrocarbon. It's made out of carbon and hydrogen. So as soon as I see a hydrocarbon, I then know my second reactant. The second reactant must be oxygen gas. I also know my products, CO2 and water, each and every time. All that's then necessary is balancing. And these ones tend to be a little bit trickier. Balancing it using that CHO method will make it easier. So we have 1, 4, and 2. Also, I forgot to mention oxygen again is Hoffman-Kleiber. That's why it's O2. Product side, we have 1, 2, and 3. Going through the process of balancing, my carbons are equal, my hydrogens are not. A coefficient of 2 changes my hydrogen to 4. This gives me 2 plus 2. So I now have 4 oxygen on the product side. A coefficient of 2 will fix that. And I now have a balanced combustion reaction. So then I just gave you one that is translating it. So again, we haven't done organic naming. So here's an example of something called octane. The reason why it's called octane is it's oct because it contains 8 carbons. Ane, if you draw the Lewis structure, it would be all single bonds. That gets into a whole nother thing that we're not covering at this point. But what I can tell you is that it tells you that it's combusted in a vehicle. So gasoline often has octane. So we have the formula for the hydrocarbon. Everything else is going to fall into place just like the combustion of methane up above. You need oxygen present. You're going to make carbon dioxide and water. Again, the order of your products does not matter. You can put water first. You can put carbon dioxide second. Whatever works for you works for me. So from there, we have 8 carbon, 18 hydrogen, and 2 oxygen. And this side is 1, 2, and 3. When you go to balance, I'm going to place a coefficient of 8 to take care of the carbon. To balance the hydrogen out, I'm going to place a 9 here. That changes this hydrogen to 18. For oxygen, I have 8 times 2, that's 16. 9 times 1 is 9, so a grand total of 25. This is where combustion can become tricky then. So the trick I can show you makes life easier for me. Again, my chemistry teacher liked to use fractions. If you want to use fractions, go for it. I won't take off for it. The idea is here there really is a coefficient. That coefficient is a 1. So what we need to do is we double everything except the oxygen, what we're trying to balance. What that achieves for us is it gets rid of that odd number of oxygen. So all we've done here is we have 16 and 16. We have 6. And 36. And then from there, we've doubled our oxygen on the product side to give us 50. We've done nothing to the reactant side. Again, 50 something times 2 to get to 50 is going to be 25. And that takes care of that one with balancing. So that's why I threw that particular example in, is when you get an odd number, you double everything except the O2. Go back through and then balance the oxygen out, and it'll make it easier on you. All right, so last thing in my long-windedness. So we have 3 mixed practice to just kind of summarize what I've accomplished in this unit or this topic. So this first one, we have C2 plus H2. It's reacting with oxygen. So yes, I see 2 reactants. However, I see that this is a compound. It's reacting with oxygen. This is a hydrocarbon. So this is a combustion reaction. So as soon as you know that it's combustion, you then know the 2 products. You know that it's going to be CO2, H2O. You can then go through the process of balancing. So this is going to be a 2 here. Hydrogen are balanced. Here I have 4 and 1, which is 5. So this is like what we just saw in the last example. This is the double trick. So you change this to 2, skip the O's, change this to 4, change this to 2. So when I do that, this gives me 8 plus 2 or 10 oxygen. Therefore, a 5 will balance that, and we are done. Here in the next example, we have beryllium plus oxygen. So beryllium is Be. It is not Hoffman-Kleiber. Oxygen is O. It is Hoffman-Kleiber. We need to determine what this is going to produce. We can see that we have 2 single elements. Therefore, this is a synthesis reaction. So I need to combine this into one product. I do that by looking up charges. Beryllium is a +2. Oxygen's a -2. Therefore, my final formula is BeO. All I then need to do is balance it out by placing a coefficient of 2 and 2 in front of the Be and BeO. Very last example then, we have silver 1 oxide. I can see, or excuse me, silver 2 oxide, and that's a typo. That's really silver 1. So silver 1 is going to be Ag2O. And how I know that is silver is Ag, the Roman numeral is a +1. Oxide is oxygen with a -2 charge. Cross down, I get Ag2O. I can see that in this reaction, I only have one reactant, and that reactant is a compound. Therefore, the only thing it's able to do is break down or decompose. So this is a decomposition reaction. So now I'm going to just separate it into my two ions, the cation, anion. It's going to make silver. It's going to make oxygen. Oxygen is the only Hoffman-Kleiber. Silver is not. Then I need to just go through my balancing process. My silver are not balanced. I can place a 2 there. When I do that, though, my oxygen are not. So I'm going to end up saving myself a step. I'm going to place a 2 here to balance out my oxygen. That gives me 4 silver. A 4 is then here, and oxygen is a 1. So, again, if you have questions, need help, please let me know. Otherwise, good luck on your homework.